All right. Hi, everyone. My name is Lucas. Very nice to be here today. I did my PhD and my master's at CCL at MIT, graduated last year, and now I'm a research scientist with OmniML. So at OmniML, we are trying to bring some of the technologies that you've been learning about into the real world, and making the vision of ubiquitous AI across different applications and edge devices a reality. And as part of that, we released our tool, Omnimizer, recently. And it's based on a lot of the technologies and the research that you've learned about. And I want to give you a little more insights about how we brought some of these technologies into production, what we see some of the problems in industry, how other people can potentially benefit from neural architecture search. And yeah, just give you like a little bit of heuristic and holistic insight into a lot of the things that we have been discovering over the last couple of months. Cool. Yeah, feel free to ask any questions at any time. And looking forward to telling you a little bit more. So I want to start with a quick introduction about our company, OmniML, where we originated from, what we are doing. Talking a little bit then about Omnimizer. So that's our platform and software for developing edge AI applications. I'll tell you a little bit about a few case studies and real-world customer examples that we have already encountered in the past few months. And finally, for the second half, I'll give you a live demo of our tool and give you a little bit of a feeling how you potentially might be able to also leverage Omnimizer in your own class projects or for any other kind of application where you want to bring machine learning into the real world, right? Cool. So let's dive into it. So OmniML was founded about a year ago, a little over a year ago. We're a startup of approximately 20-25 people by now. I myself did my PhD also in efficient machine learning, and then I joined after my PhD. So it's actually been a super exciting and fun journey for me, seeing how some of the research things that I've been working on and the broader community has been working on, seeing that put into production and seeing that impacting actual companies and consumers. So yeah, it's been a really cool journey. And overall, what we try to do at OmniML is we want to accelerate the design and deployment of AI across all kinds of devices. And the way we think about that is there's a lot of obstacles right now that many consumers and many industries face, right? And how we want to solve them is we want to help them putting AI into like a production environment faster. We want to make it easier for them to develop AI models. We want to do that in a way that we help engineers and machine learning scientists actually develop these things on their own, right? And basically, spreading and making all the kind of research experience that we have, making them available to a broader engineering audience. And at the core of all of this sits that at the end of the day, we want to squeeze the best performance out of any given device, right? Especially if you're thinking about applications that don't necessarily have an internet connection or can't rely on cloud connectivity, you have to make do with the compute resources that you have available on your device, right? So and we know that AI scales really well with data and compute. So that kind of is there's a lot of tension, and it's an interesting challenge to see how do you squeeze the most amount of compute out of your given hardware. Yeah. And what we also see is that if you move away from the cloud, devices start to get a lot more diverse. You might have actually companies who have been in business for decades that already have tons of IoT devices or other kind of devices in the wild. And so they don't necessarily always have the flexibility of choosing any hardware you want. So you really have to make what you have work and use the most out of it. Yeah, and so I've been talking a lot about this idea of making AI available on all kinds of different devices. And why do we want to do that? Well, we believe that there's huge potential for non-cloud AI applications on the edge. And some of the core industries that we currently see that use a lot of AI are ADAS industry, so autonomous driving, we also see, different robotics beyond autonomous driving that, leverages more and more AI, and it's becoming more. So if you, read any kind of, recent research papers in any of these fields, basically there's more and more of the stack that's being consumed by AI and by deep learning technology. So this problem is only becoming bigger and bigger. Yeah, and then we also have different IoT devices, right? Smaller sensors, distributed sensing that can benefit from AI. And obviously also AR and VR. There's been a lot of conversation recently. So all of these, greatly benefit from running deep learning models on the device themselves. But really, because you have this diversity of hardware devices, and you also have, when you train a model, you're mostly focused on a idealized cloud environment, right? You have your NVIDIA GPU, it's always the same. And so once you go to deployment and it gets a little more messy, you see a lot of problems coming up. So that's kind of the core problem that we are trying to solve. And the technologies and algorithms that you've learned in the class over the past few weeks can greatly help with that, right? Yeah, and so part of the reason what I already touched upon is this, gap between essentially right now research and development, or basically training a model, and actually putting the model into production, so running inference tasks, right? So any kind of production environment usually doesn't necessarily need to do too much training, right? But you have to run, tons of inference tasks, right? Hundreds, thousands of images. A robot or like an autonomous car usually processes like 24 frames per second. So it's like terabytes of data, right? Where you just keep doing inference all the time. So making that more efficient, making it easier, and also, closing the loop and, bringing the information that you gathered from inference devices back to the training environment, right? And then continuously updating the model. All of these are huge challenges right now. And so because we don't have good solutions for that problem yet, what we see is that a lot of companies struggle with bringing AI into the production environment. So it takes a long time for them from, researching to actually putting something into production. At the same time, because people, don't know how to solve this problem, we also see that people end up, with inferior models, because although they can potentially, get models to train really well in open source or cloud environment, they don't necessarily are able to put these same models on their actual, production inference devices. And finally, that's also, if you think about it from a business perspective, right? If I'm a VP or some other high level decision maker, would I necessarily want to invest in a field where I don't know what kind of business outcomes I can produce, right? Imagine, we have this vision to have AI everywhere, but if now you have to trying to implement it and actually it takes you maybe a year to get to some prototype and then you don't know if it works yet, right? So this is actually a huge, obstacle in, having businesses invest more into artificial intelligence and deep learning technologies. So that's kind of, what we hope to solve. And let me tell you a little bit more of why, we believe that this is currently such a big problem. So if you think about it, how we develop AI models today, and, you might have done some of that, but it's basically pretty much all is on the left, right? You have some kind of task specification, let it be computer vision applications like, image segmentation, object detection, obviously image classification is this very simple one. And then you usually kind of, you train your model, you develop it, you usually have your cloud GPUs where you can, easily train a model, usually compatible with your favorite open source framework like PyTorch or TensorFlow. But you don't really think about, what comes afterwards, right? And what comes afterwards is that you have some kind of deployment scenario in mind, right? For example, you have a robot and, some other team purchased that robot, or maybe, designed the robot themselves and they made a decision, okay, we're going to put this hardware chip in the robot. Now you're actually faced with the problem of how you're going to make this AI run on your robot, right? And right now, what a lot of companies end up doing is that essentially you have a separate team that is aware of the deployment environment. And now you have this process where people start essentially manually communicating with each other over long time horizons. And you can imagine that this manual process, first of all, it's slow and tedious, but also that because you don't have any way of like, gathering high, instant automated feedback at this stage during the training, you actually might end up with a model which is not really suitable for your production environment. So a lot of people just ending up, optimizing for accuracy over and over again. And you also see that in the open source and the research community, right? Like the moment we have a nice data set and you have some kind of challenge where you can post on a leaderboard, right? A lot of people end up, optimizing for that kind of leaderboard, which is not necessarily reflective of what you'd see in the actual production environment. And yeah, so you end up with models that might not actually, fit well to your hardware device. And because your hardware resources are limited, it's not like in the cloud where you can just add another device and all of a sudden you have double the compute power, right? It's your robot and there's your robot and that's all you can do. Well, I think what we believe at OmniML is that when we, get rid of some of these obstacles, we actually end up with a model that is, smaller, well-fitted and faster, and also gets you the performance in terms of the accuracy that you want. So how do we envision we can change the existing workflow and how people think about it, right? So like I said, right now we have these slow manual feedback loops and production loops. And what we want to do at OmniML, we want to kind of like revert this problem. We want to basically, introduce a tool and a cloud native environment where when the ML engineer develops and trains a model, or you as research scientist, you don't have to necessarily, hope or like just estimate or guess what your deployment scenario is. We actually provide you with a cloud native environment to essentially, not only train your model, but also test your model in your deployment environment. And now what's really cool about that is, you can not only do that once, because now it's really fast, you can actually do that many, many times, right? And so imagine how that changes your perspective of how you would develop a model, right? Whereas before, you might, just develop your model in isolation. At that point now, you can actually develop your model and have constant feedback of how your model performs in the actual inference and production environment. And so that gives you a totally different perspective on the problem and actually, empowers you to not only think about the accuracy and the training time, but also the inference performance. Cool, yeah. And so before diving into more detail about our product and how we actually, realizing that vision, I want to just give you a quick teaser about, one customer that we've been working with. So they're using a DDRnet 39. It's basically a image segmentation model. And what we have done is we applied the platform and the software that we developed and tried to help them optimize their model. And so I'm going to give you two numbers here. So one of them is, optimizing that model with, a NVIDIA Orin device, and the other one is with a Qualcomm S888 chip. And so what you can see here is that there's actually, especially for the Qualcomm device, and that's basically this device here, just a phone, the original model is really not well optimized to run on that device. And by using our tools, you can actually get an over 8 times speed up for that model, so that you essentially can match the performance of a much more higher performance chip from NVIDIA, the NVIDIA Orin. And that's super exciting because that shows you that, you have a lot of flexibility the way you design a model, right? And because you are designing it in a cloud environment, you might not necessarily make the best design choices. But having that feedback loop and having, Omnimizer in the background, what it actually enables you to do is like make much better design choices, some of them which are automated, right? So you don't even have to worry about it. And you actually get that, over 8 times speed up, which is, I think, super exciting and thrilling. You can also see that for NVIDIA devices, the gap is not as big. That's expected, right? Because this is essentially a repackaged cloud GPU, right? So the model was usually trained on cloud GPUs, so the performance is much closer. Yeah.
What was the task? What kind of task is 300, 500?
Well, let's put it this way, this might be one network out of many that runs on a device like that, right? So you don't necessarily need 300 frames per second. But imagine this to be one of maybe 10 networks, right? And then you're like down to 30 frames per second, and that's much more reasonable. So this one was tested in isolation, right? Without any other software running on the device. But usually you not only have your neural network running, you have pre-processing, post-processing. In robotics, you know, the deep learning pipeline is usually only parts of it, right? You have motion planner, everything has to run on the same chip essentially, or a collection of 2 or 3 chips.
So does your product only optimize with the neural networks and also optimize with like other pipelines like the path planner?
We are focused on the neural networks, yeah, which usually take up the biggest chunk. And also that's where you have lots of ability to optimize. Cool. Yeah. Yeah, so that's basically what we do at OmniML. Now, like I already teasered, is we over the last year we developed a platform for other people to use and be able to like optimize neural networks, and that's called Omnimizer. And so I want to now give you a little bit more in-depth view about our platform Omnimizer. Cool. So going back to the picture of what we already discussed, is essentially that right now people develop in PyTorch, and there's this huge gap in order, for people to actually deploy machine learning models. Now, how we envision closing that gap is by essentially introducing a standardized layer on top of that, which we call the Omnimizer engine, which essentially allows you to query any of these devices in a way that you don't have to worry about how they operate, what kind of operating system, what kind of tool chain they have, right? A lot of these hardware devices have different tool chains. Some have like CLI interfaces, some have Python interfaces, some of them, have all kinds of different pipelines. So the idea is that, we kind of raise the level of abstraction so that no matter what device you choose, it actually becomes easy for you to, just interact with. And then the second part is, and that's closer to what you have learned before, is the core Omnimizer library, which essentially is a PyTorch plugin, so to say. So it's fully compatible with PyTorch, and it is essentially enables you to what we say omnimize your training pipeline. So essentially, you can modify your model, omnimize your model, and then during training, you get the benefits of a lot of these model optimizations and the hardware feedback loops. Yeah, and basically what you get with that is you have a standardized interface. Every time something is standardized, it makes it easier to use and faster. We always want faster and easier, more iteration time, easier to develop. You can try out a lot of things. Another thing that's a big concern for us is, we all love open source tools. So we want to make sure that, our tools are transparent and they also integrate with existing open source tools, right? So that's important for us. And yeah, so that's kind of how we think about the problem. And we also, looked at some of the current approaches in industry. So there is other approaches about, that use NAS as well. And just want to tell you a little bit about how we, think about them and what we can, provide on top of that. So I want to quickly mention 2 tools, like one is from Microsoft and one is from Google. And so basically the NNI library from Microsoft is kind of like a open source repository that lets you try out a lot of the state-of-the-art pruning and NAS algorithms and also quantization. You can take a look. You probably recognize some of them by now. There's also this tool called Vertex AI NAS from Google. It's essentially a black box optimizer within Google Cloud. And I think in your first NAS lecture, you learned about kind of like some of these early approaches in your architecture search, kind of like which are essentially a black box optimizer where you can, run evolutionary search, and every time you try a new configuration, you essentially train it. So this one works a little bit like that. And we took that one step further. So what we want to provide you is not just, a collection of algorithms to play with you, but we actually have a, highly curated list of model optimization and adaptation algorithms that don't require you to do your own research. Because a lot of these algorithms, what you find out is that they behave very similar in practice, right? Once you move away from benchmarks. And so instead of overwhelming the user with different choices, we want to make it easy and more accessible to them. Another big aspect which, makes it very challenging, especially as a, seasoned machine learning research scientist, but not necessarily a seasoned engineer when it comes to model optimization, is that you have to think a lot about how you set up your problem, right? So for example, you've touched a little bit about then, but this idea of like designing a search space, right? So if you just want to do ResNet on ImageNet, that's easy, right? Many people have done that before. You can just download a model and they give you the right search space. Or like in the case of like, Google's Vertex tool, you essentially have to, design a cheap proxy task so that each of your iterations doesn't take days, but you can actually run it more quickly. Well, problem with both of those is like the moment you move away from benchmarks, you're really on your own, right? And so we want to make that essentially easier by just giving you the ability to reuse the existing training environment and essentially, abstract all of these components away. And, just, you can train it out of the box, whatever you have, and get the model optimizations this way. Cool. And then finally, I think what we have, seen many times in our experience and also is that if you don't consider hardware in the loop, actually the type of optimizations you can do can be very limited. Where it becomes really interesting is if you think about what is my production environment, what's my chip that I want to deploy my model on, and how do I, get feedback while developing my models. And that part is, I think a key in closing the loop, right? If you think about it, whenever you design an algorithm, you can take an action and then you get some kind of feedback. And so really what gives us the ability to get accurate feedback is this ability to do instant deployment and hardware in the loop. Cool. So I already talked about this example a little bit. Now I want to dissect it and show you how we actually got to that result using Omnimizer. So the first step is very straightforward. All you need to do is essentially import our tool, and we provide this very simple interface where you can query from our available devices and get the on-device latency back. So in this case, what actually happens behind the hood is if you specify you want to query the latency on an SSA chip, is the moment you call this function, actually your request gets sent to our hosted services, where we actually host a fleet of target devices. And if you want to do that on your own, it's literally as simple as that, right? All you need to do is once you have your model is implement these 2 lines of code and you get instant feedback. Just to give you some perspective on this is most customers that we talk to, they usually it takes them about a couple of months to get a development board for one of these chips because we have chip shortage. So they want to start developing something, but they can't. They just have to wait until they get a device. And then on top of that, once they have the device, depending on the type of device, you might spend another week or 2 on the device setup. Actually, maybe the machine learning engineer in another use case didn't even have access to that device. So he was just guessing how good the model works in the production environment, right? So, and that's how you end up working a lot of times. But here, literally, we reduce this multi-week process to like a simple Python call from your training environment or Jupyter notebook. And yeah, so going back to the numbers, so in that particular instance for that DDRNet, we got a baseline model which had latency of about 18.5 milliseconds. Oh, and by the way, you can also see here, that's also something you've seen before. You can essentially specify your precision. So it'll actually do quantization in the background for you. So you can put in a FP32 model or FP16 model, and that's fine. And it'll actually get you the precision that you want. Yeah.
What level of interpretability does the service provide? Like, let's say you call this on multiple devices and multiple precisions, and you like see the latency is like different on these devices. Like, is there a way of like sort of interpreting why that is through the library, or is it still up to sort of an ML engineer that like take that process?
I mean, it's a combination, right? I think first of all, if you compare between devices, depending on how powerful they are, right? I mean, there's huge differences, right? How powerful they are. So it's sometimes a bit hard to compare between devices, right? But there's certainly there's ways you can standardize that measurement, right? And we provide that essentially something like hardware utilization or energy efficiency. So there's these ways of like standardize and normalize measurements across devices. And actually, also your question kind of brings me to the second component. So the first thing we can do in optimizing a model is let's not even worry about training or anything like that in the first place. Actually, there's lots of operations that you can just do on the graph level. So if you think about a neural network, essentially it's a giant computation graph, right? And so now if you want to run inference or training, it doesn't matter, right? The question is, how do you take this computation graph and map it onto the hardware? And now if you are a hardware provider, you have this super hard challenge you need to solve, that whatever computation graph is thrown at you, you essentially have to run it, right? And so you can imagine there are certain models that are very well optimized. ResNet is the prime example. Every hardware vendor wants to optimize and compete on the ResNet benchmark. But the moment you move away from these standardized networks, it might not be as easy anymore, right, to efficiently map your neural network onto the hardware. So what we do and what we provide is essentially a way for you to, automatically profile your model across the different operators, and also, provide a library of like standard modifications and model adaptations that, are likely to reduce, to give you quite a big reduction in latency depending on the type of operators. So in that particular model, we essentially profiled the DDRnet, and we, this is just a, comic graph, but essentially will give you like a breakdown of the latencies of the different operators. And then you can call this adaptation algorithm, which essentially will give you a list of optimizations and return you a new model that's more or less functionally preserving, but gets you so basically because it's functionally preserving, it'll, return essentially the same training accuracy, but it's much faster to run on the device here. Yeah.
So how do you get this number? Do you have a simulation of some devices?
No, it's actually run on the device.
Do you have one device?
Yes.
And you connect?
Yes.
So in order to add more devices to your library, you have to buy them.
Yes. Yeah.
And then how do you adapt them? Like how is it done?
How it's done? You mean like in terms of the software, how we choose which adaptations we do, how we choose them? Okay, so basically it's a mix of an automated algorithm and essentially a library, or like a bunch of like a list of templates of what are common architecture modifications that you can do, and then we essentially automatically iterate through them, right? And essentially look at different metrics. One of them is hardware utilization. Another one is overall latency, to understand how we can potentially improve the model.
And since you're actually adding devices to the server, then is it possible that someone has the device, you don't have it, they connect to your application?
That's something we're currently thinking about, yes. So right now we only support the devices that we have. And let's put it this way, there are a lot of edge devices, but it's not an insanely huge number, right? We usually say there's maybe like 10, 15 devices across 3-4 hardware vendors. So it's manageable in terms of like the complexity. But of course, there are customers that either have devices we don't support, or they might not want to, use a cloud environment and they'd rather keep everything in-house, right? So essentially, the way we set up our infrastructure is that the moment you add a device, right, there's essentially a standard procedure. And so whether that's plugged into our server or that's plugged in somewhere else, right, doesn't make too much of a difference as long as you can, communicate with our central dispatcher, so to say. Yeah.
How long do these calls take? Is it pretty instant or does it take a while?
So like this profile call, usually, so you have to think about it. You have to send the model right into the cloud. That's usually very fast. That's not an issue. Usually the biggest slowdown is, you can see, like, the actual inference is also tiny, right? And then obviously repeat it like a couple of thousand times, and it's still super fast. The part that takes the longest is actually calling the compiler. So these compilers have all kinds of graph optimization and graph fusion tricks and algorithms that they apply, right? The most typical one is you can actually fuse the typical convolution batch norm plus value activation into one operator, right? So that saves you a lot of time. So we have to run through these optimizations every time in order to get accurate latency estimates. And that takes anywhere between 10 to 30 seconds to a couple of minutes. So that's the main component that we kind of can't get rid of, right? So that part just takes as long as it takes.
But you're comparing to a matter of weeks.
Yes, exactly. We're comparing to a matter of weeks, and we are comparing to something which is manual before, right? I mean, machine learning, like deep learning and model training, isn't instantaneous either, right? So most people do have some kind of setup or environment where they're used to, waiting a couple of, hours, couple of days, couple of weeks for the results to come in, right? And so adding these kind of automated calls into that training loop doesn't really change the picture for them, right? And as you said, yeah. Okay, yeah. No, go ahead. Yeah.
Oh, I was just gonna ask. I don't exactly see where any data is loaded here. So is the inference done just on random inputs?
Oh no, that is dummy code. Yeah. So usually need to provide an input. That's also something that we've worked on very extensively. And it's not shown here. Is that a lot of these hardware devices or tools define their own way to process input data. So especially if your input data is maybe not just an image or like a tensor, but maybe a combination of tensors, it gets really confusing because each toolkit kind of decides on their own how you provide multiple tensors in a row. And what we have done here is we have also made that easy in the sense that you can just call the model the same way that you'd expect it in PyTorch. But yeah, definitely. And then also you can have, you can change the type of results you get, right? So usually whether you run something with batch size 1 or like a larger batch size makes a big difference. So you can also basically influence your feedback and your results by giving the appropriate input, right? Some people, like if you think about robotics, you need to do usually want to do batch size 1 because the moment you get a new sensor signal, you want to process that immediately so that you can inform your motion planner and other downstream tasks. If you have something where you can wait a little longer, you can do batch computations, right? I don't know if you use Siri on your phone or other voice recognition systems. You don't necessarily need to process each word individually. You can kind of wait, batch them together, then run inference. Cool. Yeah. So that's pretty much like the the first part where you just before even you look at training, right? You just start profiling the model, understanding what is your production environment, how can you even optimize your model before you do any kind of training. And it's super exciting because the alternative would be you just train the model, then you try to deploy it, and you realize there's something very obvious you missed in the beginning. All right, yeah, and then kind of like the third step in kind of like our idealized pipeline is when you get to the training part. And just like before, we actually provide you with a simple one-liner that actually makes your model so what we call elastic or flexible. So essentially after that line, you get a model which is kind of like a search space. So it represents a collection of models that you can activate. You can sample different models, and also what we also provide as part of that is essentially it natively integrates into your pre-existing training pipeline. So if you already have some kind of training script, you can now actually just call your training script with the Omni model instead of your original model, and it'll actually get you the same benefits as NAS or pruning. And specifically, we have developed 2 flavors of NAS that automatically, work with your training loop. One is more, a kind of like more expensive version of NAS where you have to like increase your training time, but you have the benefit of essentially exploring a larger search space, right? So you can do more, you can essentially get a better output at the end at the cost of increased training. And also, if you just want to do, quicker experiments or training for long is, not an option for you. Some training tasks take a week or 3 weeks, then, at that point, it kind of gets tricky to wait that long. If it's just 1 day, if you want to wait for 3 days, I guess, that's fine. But essentially, it comes at the cost of a reduced search space. And no matter what you choose, you can just, it's just like this one-line change, and then you train it, and it, gets you essentially a trained search space or like a trained model that you can then specialize for your deployment. Cool. And then the 4th step is essentially the post-training search, right? So now we have trained this collection of models, but we still need to pick one that will actually then run on the device. So for that, what we want to do is we want to essentially search one that has an optimal accuracy latency trade-off. Or if you can also specify other type of constraints here, we have latency, but you can also think of it, you just want to, minimize memory footprint, or, something like floating point operations. You can also do that. And that essentially, will explore the available architectures and the available search space, and essentially, sample different architectures, measure the accuracy, and then, depending on the constraint you set, pick the one with optimal trade-off. All right, so that's kind of like the, the architecture search part, which is, a simple 3-step process. And then finally, you can go back to our engine. And now you can actually also, test your trained model and compile it. So we give you the option to, compile the model, keep a local reference. And then, for example, obviously you can compute latency again, but you can also just run inference on the device model. So if you run inference here, instead of running it on your local GPU or CPU, actually your, input will get sent to our cloud and then actually run natively on the device that you choose. Yep, and at the end of this process, we kind of get this 6 to 8 times speed up that we mentioned in the beginning. And yeah, and of course, all these numbers are without essentially negligible loss of accuracy, or within like measuring noise, because yeah, always important to say it, because you can obviously make architectures a lot smaller if you neglect accuracy drops. Cool. Yeah, so that was that part. Let me guys give you just a summary of the what we just saw on our DDRnet. So we started out with kind of like this model, the original model, and we tested it on 2 devices. So these 2 devices are actually quite different. So peak tops is kind of like how many operations this device can do per second. And you see that actually the phone is much less powerful than this orange chip. But after we adapt the model and optimize it and train it, we actually essentially get to the same performance in terms of frame per second on this much less powerful device. And if you kind of like think about it in terms of efficiency, we went from like 1/3 of the efficiency of the Orin to about 3 times the efficiency of Orin, right? And this part here is really, showing how not only doing model optimization, but also closing the loop with the hardware device really helps you getting a model that has the optimal latency accuracy trade-off on your desired target device. Cool. Yeah, and to recap, what does Omnimizer do for you? So we kind of have two components that we talked about. Omnimizer NAS, so the model optimization component, and the engine. What we provide with the NAS interface is essentially a PyTorch native model optimization library. You can just integrate it into your existing training pipeline, and you can also then immediately just search for the optimal subnet. And then with the engine, you can also take all of these models that you're designing here, and you can deploy them. You can try running on-device inference, and you can do profiling from Python, and all of that without touching any other kind of like crazy toolkits, right? Because the thing that we hate the most is installing something. Yeah, that's pretty much my high-level intro about Omnimizer. Do you guys have any questions at this point? Cool. Yeah.
I guess from like a business perspective, do you like charge for every call, or how do you like make money?
So right now, essentially, we essentially provide enterprise licenses. So we work with enterprises that usually have quite a large operation in the sense of they have a lot of devices or quite high scale. And so for them, any kind of optimization is really powerful. And so we usually give out enterprise licenses, and then also essentially work with their engineering team to help get accustomed to Omnimizer. But it's we are early stage startups, so that's up for change. There's many different ways that we can go. You might see a lot of other startups go the open source route, right, and then charge for premium services. So there's different ways you can monetize that. Right now, kind of our main focus is providing value to the enterprise customers we have, while making good progress and increasing the scope and the footprint of our platform, and making it more useful as we go and grow. Yeah. Mm-hmm. So right now we're focusing on the first one, so chips provided by us, but it's something that we're currently exploring and discovering, right? It makes it a little more tricky in terms of like the engineering challenge, right? Because right now, how do you make devices communicate and things like that, right? No, they're running sequentially, so that you have a reproducible, accurate environment, right? It's actually not that easy to make these things reproducible. If you think about it, if there's some, if the AC in the data center doesn't work for like half an hour, the chips are going to overheat, right? You have all of these things that can actually greatly affect the performance and these measurements. So at least what we can do is control our environment as much as possible, right? So we don't run things multi-threaded or in parallel. Essentially, the way you can think about it is you can either run it sequentially, or you start buying more and more devices, right? So that's another aspect that basically you can parallelize across having multiple devices. I mean, these chips are like expensive, but they're not insanely expensive, right? So you can purchase multiple of them. Cool. Yeah. Now I want to give you a couple more examples of how we used Omnimizer in the real world with some of our customers. So I'll give you a quick example. This is a YOLO-X model. You might have heard of it before. It's essentially a state-of-the-art model for object detection. Runs really well on NVIDIA cloud GPUs. But again, similar story. We looked at the how we can, improve the model, and, essentially found a way to like improve it by 50% with the tools that I presented earlier. So there's no other, manual optimization on top. That's literally just, using the model adaptation and optimization algorithms that we provide. And similarly, you can also see speed ups on NVIDIA devices. Again, and I think that's, again, interesting to emphasize and mention is we do see speed ups, not quite as drastic as on other devices, just because they are more powerful and they're closer to the chips that you would see during training. So that really shows you how important it is to adapt your model to the specific hardware, right? And for NVIDIA in particular, because everyone is using training GPUs that are based on NVIDIA chips, it's different there. Cool. Yeah, we can also dive a little bit more into detail about some of the numbers, which are, I think, super interesting. So again, we have the first one and the third and the fourth are different Qualcomm chips. This is another NVIDIA chip. So basically you can see, first of all, you can see that in terms of like their, overall performance, it's quite drastically different. This is, where you get into domains where it starts measuring how much compute you have. And then you can see, optimized version, you can see the speed ups. I think it's also interesting to see like some of the, energy comparisons, where essentially for example, this is a robotics platform provided by Qualcomm, quite bad energy efficiency, even compared to like NVIDIA devices. But you do get it up to almost the same, energy efficiency using our tool. Also these other chips, again, they're actually very efficient. They're the ones running on your phone. So they want to be energy efficient, right? But again, we can like, essentially almost, add 50-60% energy efficiency to them. And the cool thing is that, that's all with the same accuracy, right? And also an interesting way to think about it is if you're not interested in improving your efficiency, you can also improve your accuracy, right? Let's say you're happy with your latency like that, right? But you're not happy with your performance, right? So that's another way that you can use these tools. It's not just about improving the latency, but you can also think about it as improving the accuracy. Because at the end of the day, you're improving the Pareto curve or the trade-off between accuracy and latency, and so you can pick and choose your favorite point along that line. Yeah, another kind of like model, it's a monocular 3D detection model. So essentially you go from one camera to 3D predictions. Again, just to emphasize a little bit like the, breadth of different applications that you encounter that are usually not based on ImageNet classification. So, that's something I think as a, researcher or like somebody writing papers, it's always hard to imagine. But I think it's super important to, see the breadth of different applications out there. Again, we tested it on different devices, see, consistent speed ups. And that one, we also, like some of these models that I presented, we also actually put on a robotics platform. So this little, robotics RB5 show platform from Qualcomm. It's a, super cool platform that you can, play with that, is a good prototype. Obviously, although, not a fan of ImageNet, but everyone needs their ImageNet ResNet example. Yeah, you also get, improvements, kind of like have 70-80% accuracy usually with ResNet these days. So on top of that, we can still, improve the performance, which I think is still interesting because ResNet is probably the most well-supported network of them all, together with VGG. For hardware devices, kind of if you imagine you're a chip developer, that's the first thing you want to do, make sure that you perform well on ResNet. So even on top of that, we can still perform, provide some value, which, I think just, shows you the power of pruning your architecture search and any other kind of optimizations. Yep, and a final one, also kind of a cool application is, optical flow networks. They basically allow you to, estimate how pixels or objects are changing over time. Super cool. And what's interesting here is like we actually get a, 2.5 speed ups, even on like a T4. So T4 is like a cloud inference chip from NVIDIA. So that's also, really interesting. And I think also really interesting for you as students and researchers is that the more you move away from benchmarks, the less likely it is that a lot of these models have been hand optimized over years. And, that also just amplifies the power of automated model optimization algorithms here. So let's start with the second part. I want to give you a quick live demo. Well, not too quick, depending on how much time we have. But I want to give you a live demo. The reason why I want to give that to you is because, like Professor Han mentioned, you also have the ability if you want to get access to Omnimizer. So I want to give you a quick overview of how it works live on a simple ResNet CIFAR example that you can run in like Google Colab. So maybe I'll sit down. So because I need to like type, but yeah, let me pull up the time with the camera. Yeah, the Colab. So let's walk through the steps how you can actually use it. No pseudocode here, so all the inputs are there. Yeah, first step is obviously you want to install it. Right now we require you to sign up and get a username and password. Then here you can just, download Omnimizer, install it. Takes a couple of seconds. Cool. We start the runtime. Yeah, then we just have a couple of imports. And here we just defined a CIFAR10 dataset, also very standard. Same with the model. It's just a standard ResNet 20, 32. So a fairly small model, only has like 500,000 parameters, but makes it easier to use. Yeah, then we just have some training utilities. So here you can kind of train a baseline model. I'm not gonna fully train it now. Google Colab is great, but not that fast. So I'll just let it run for 3 epochs. But like the online version has about 120, gets you to over 90% accuracy on CIFAR. Yeah, so that's kind of like, that's no Omnimizer here yet. That's just like, training a regular ResNet. But yeah, now we can get to that part where you can actually start using Omnimizer. Like I mentioned in my slides, they're kind of like, there's the model adaptation feature. I'm going to skip that one because the public version right now doesn't have that in it yet. And we're going to, focus on the 2 neural architecture search algorithms, AutoNAS and FastNAS. I'll give you an intro to FastNAS since it's a little faster, and then we can walk through AutoNAS, which is, like I mentioned, more accurate, but also takes a little longer to train. So yeah, this one is almost done, but let me go down to the FastNAS part. So yeah, first one, now that we have installed the library, we can just, import Omnimizer. And the next step is essentially now we have a ResNet 20 model. We trained it a little bit. I think the accuracy is probably not great, but yeah, 54%. So not exceptional, but I think it's fine for the demo. Yeah, so then you can essentially just run this model. It'll perform essentially this Omnimize step in the background, and now your Omni model is a new model, which is essentially like an elastic model. So just maybe I can give you a quick, idea how it looks. But if you print the model now, you'll actually see that. Oh, it's a text cell. Sorry. Just a ResNet, but it has these dynamic blocks. And if you look at it, what you can do now, for example, I can essentially choose the minimal network and run it again. Now you can actually see that we changed the number of channels and reduce the overall model size. It's still a native PyTorch model. So you can essentially just directly activate different models and then just use them as you would a regular model. This is super cool. And essentially all you need to do is, call this one line. Now, let me also give you a little more, insights. So we can actually also, profile the search space that we generated here, the Omni model. In this case, we'll just profile it for floating point operational parameters. So we don't have to wait for the server to respond, but you can also, choose a device so that it shows you latency. And so you can see here is that the original model has about 14 million floating point operations. And after we optimize, you now have a range of models, which is essentially between 24 and 50 million floating point operations. That's kind of like the standard setting that we choose. You can obviously also optimize this range. So depending on where your constraints are, what your base model is, where you want to end up, you can also customize this, and we provide a bunch of tooling to help you kind of like get into the range that you care about the most. Yeah, so this is essentially, we also, part of this, toolkit, which I think is super exciting, essentially analyze the model in the background, and we're trying to figure out what are the dependencies so that we can, accurately change the model. Cool, yeah, so because we picked, we already pre-trained a model, and in fastness mode, we can actually just use this pre-trained model to directly search a subnet. So again, I'm just going to run it for a couple of iterations, not too long. Usually we, take more iterations, but here we can just maybe do like a couple of iterations so it doesn't take too long. Oh, actually, I don't need that. Never mind. This one is fast anyway, because it's, so here actually we can run the full search process. Essentially, it's going to evaluate the validation accuracy a couple of times, and then based on that, decide the correct subnet depending on your constraint, right? So here in this case, we specify a flop constraint, and here again, that's what we mentioned before, is you need an input, right, to measure these things like floating point operations. In this case, we just pick batch size 1. You can also play with the batch size here if you want to make it smaller, bigger image, right? So totally up to you. And after we measure sensitivity scores, now we can actually do the NAS search and wait for it to finish. Done. Okay, cool. So this case, because we didn't train it very well, it even found a almost better architecture than the originally trained network. That's usually not the case if you properly train it. But in this case, like, the accuracy numbers are obviously a bit off. Cool, yeah. And then the final step is, fine-tuning. Fine-tuning is always a great idea. If you don't know how to improve your model, you can always just add more training to it. It usually helps. Again, just fine-tuning it for a couple of epochs, but basically that would be the final step. And we can now just, while we wait for this to finish, you can see that here you can just reuse the same training function as before. So it is essentially super easy to use, right? That's the original training function. We used it once with the anonymized model. Now we use it once with the searched model. And then once you're done, you just get your final network. And that's it. Then obviously training can take longer, but that should give you an overview of how it works. So in this case, now we can go back and trying to compare the model. And so you can see that in this case, we reduced the number of floating point operations from 40 million to 30 million. And if you actually trained the model to completion and went through the whole training process, you'd actually find the model has about the same accuracy as before, and 25–30% less floating point operations and parameters. So that was a quick overview of the fastNAS part. Do you guys have any questions now? Just try it on your own if you don't have questions. Yeah, so that's that part. AutoNAS works very similar, except that you have to do a little more training. So I won't do any training there, but just quickly show you same process. One thing which is interesting to mention is because with AutoNAS we do more training, but we also have a bigger search space. You can actually, if you want to, start with a bigger model to begin with. And because we have that more flexibility, usually if you start with a bigger model, you get better results, which is super nice. So that can be like super powerful. And we're actually working on something right now to kind of automate this process as well. So you don't have to like think about which model to start with. And that essentially gets you into the right range in terms of parameters and flops or latency. Again, yeah, you can also, profile the model here. Like I mentioned, here the search space is much bigger. So essentially here we have, a search space that varies between 4 million and about 68 million flops. So it's about like a 17, X difference. So there's lots of ways for you to, specialize that model and optimize it for different deployment scenarios. And then in this case, we actually need to train the model from scratch. We also should, train it for longer. You still get to about the same accuracy after that. And then again, as before, we'll also do the search. In this case, actually, if you, probably that doesn't run now, but if you do run the search, it actually takes a couple of hours, because in this case, we actually, evaluate each subnet more extensively so that you basically get closer to this optimal trade-off. And then something else that we worked on kind of here is also pretty cool. This is essentially a way for you to, after, you might want to restart an experiment, or maybe you have different scripts or different ways to interact with your model. We actually have this simple, it's kind of like, imagine it like torch.load. But what it does is it starts from your base model and actually then recreates the modified architecture and loads the checkpoint. Because you now have a different architecture at the end of the process, right? You can't just load the wait checkpoint. You actually also have to, make the modifications to the architecture every time you create the model. So this is basically just an easy way for you to get the searched model back from your base architecture. And then also for AutoNAS, we essentially tune the model, fine-tune the model afterwards. And here, we picked the same constraint. So we wanted to get it down to 30 million floating point operations. And here you can see that, AutoNAS actually gets you higher accuracy than the original model and higher accuracy than fastNAS. Yeah, that's pretty much it. That's kind of like our tool in a nutshell. If you do sign up, second thing I want to mention is like you will get access to our portal. And so then you can just sign in. It'll give you a, we have documentation. It tells you how you can install it. And yeah, so that's pretty much all I wanted to show you guys today. I do want to just spend some time wrapping up. Yeah, so coming back to this picture, right? So I strongly believe we will make here if you want to deploy in the edge by bringing this additional abstract into the pipeline, making it easier for you to optimize the model, receive feedback on your deployment scenario. We envision it to be flexible, scalable, and automated. Just pick your favorite model, pick your favorite training pipeline, and supposedly works out of the box, right? Asterisks there. We already explored this in a lot of different contexts. I showed you some of the use cases. We have customers in autonomous driving, in the IoT, robotics, mobile space. And yeah, so it really comes down to like, how do you make it easy enough for people to, maximize hardware performance? Because, that drives costs, that drives, applicability, that drives the range of applications that you can think of. Because there's always this threshold where if you're too inaccurate or too slow, it just changes the business model, it changes the nature of the product. And so really, you got to get to that sweet spot where it becomes viable to run machine learning on the edge. And we want to help you get there. Cool. So I already teased that, but if you guys are interested, look us up on the website. You can get access, you can sign up. Please use your MIT email address if you do, so we know you're working on a class project. And also for anyone who is interested, obviously we are growing, and we are interested in hearing from you if you're also interested in working closely with us. So yeah, that's pretty much all I wanted to tell you. And yeah, I hope you learned something today. I can tell you it's a super exciting space. I love it. And yeah, love to hear from you guys, or if you have any questions, I'm here. I mentioned before, we have a bunch of phone demos, and yeah, feel free to check them out. Cool. Thanks so much.